Imagine being able to explore every single path through an Android app, not by clicking buttons, but by letting your computer solve the code itself. Welcome to the power of symbolic execution. Unlocking the secrets hidden inside a compiled Android binary isn't just for elite hackers anymore. In this video, we will be diving into OWASP MASTG Tech 0037 to show you exactly how this technique works. We will take a real-world Crackme challenge, which is complete with tricky ARM assembly and hidden logic, and unleash an advanced tool like Anger to literally generate the correct license key for us, where we will be finding out what data the app processes, how it hides its secrets, and whether your app is safe from this next level automation. If you want to move beyond basic static analysis and master the technique that security researchers use to break the toughest apps, stick around. This is the practical demo you don't want to miss. Imagine a bug in a very large code base that will only show up when two variables meet in a very rare condition. We can never hit it through fuzzing or random testing. So we need something else to figure this out. And this is where our symbolic execution comes into the picture. We will learn what is symbolic execution, how does it work, why it is useful, where it can be used, and a small demo where we will be using symbolic execution to create a keygen for an application in Android. So this is a Crackme from OWASP for Android. Shall we get started? So let's start by understanding what is symbolic execution. The sound of the word may feel it might be complicated. Yes, it is, but let's try to make it simple, at least to understand the concept. So, what is it? Symbolic execution. So, in order to understand what is symbolic execution, we need to understand how a program runs, right? So, normally, whenever we run a program, any computer program, Python, Java, anything, it takes certain values as input, and based on the conditions that we have, it starts executing based upon the match. Now let's take a small code example in order to understand how a normal program works. So to keep it simple, we will have this in Python so that everybody can follow and understand. In this code example, we will take a small if condition and print if and else case respectively. X equals to 5, and if x is greater than 0, then we will be printing it's positive, else we will be printing it's negative. Now if we see x is having a real input which is 5, based on this, even without executing, we can say that it will be executing only this statement and it will never execute this. Let me make it big. So we have a variable x which is already defined, whether we look at it or even if we execute it, we know that this code will execute only this particular condition. So here we have the variable x equals to 5, which is the real input, and the program will be printing it's positive. Now let's try to understand what happens in symbolic execution. This will give us an idea about what is symbolic execution, right? So in symbolic execution, instead of using real numbers like 5, we will be using symbols in order to represent possible inputs. Hope everyone have learned maths, right? So you know that all assumptions and imaginary variables that we use to solve the equations, similar concepts, okay? We don't assign any value, instead we assign some symbol. So in the place of 5, let's say we replace with x or y or z, you can take it anything, okay? This is just a placeholder which is a symbol. That's how this execution gets the name symbolic execution, right? Because instead of real values, we are using variables or symbols. The program doesn't run with just one value because this variable does not hold any real value. Instead, it holds a symbol, because of which it will not run just with one value. So instead, it will try to run all the possible paths or tracks. Now, the program doesn't run with just one value. Instead, it will track or explore all the possible paths the program could take without giving any specific real inputs, right? So if x, for our understanding, let's replace this with the given symbol x rather than a variable. If x equals to 0, what happens? It will go to the else statement and print its negative. This is one path. If x lesser than 0, what happens? It will again go to the else statement, else loop, and then it prints this statement. If x is greater than 0, then this will go to the path which prints it's positive. So that means with symbolic execution, without giving any real values, we can identify all the possible execution paths. This is the execution path, one path and the second path, right? So for code, for this code, we have two execution paths, which we may not trigger, right? Try to remember what we started the video with. We said that if we want to find a bug in a very large code base, that will only show up when two variables meet in a very rare condition. Now, if you are always giving a real input value of 5, 10, 20, 100, it doesn't matter. It always executes this path, right? And you will never get this unless you try something else. Now, it's a smaller condition or simple condition which we can think and we can give it during testing, right? But this will not be the case in all the programs. Most of them will be more complicated. Now let's understand why this symbolic execution is useful. Why are we even talking about this? First, it can be used to automatically discover all the possible cases where the program can crash. So in simple terms, we can use this to find the bugs. Second, we can use this for generating the test cases. Uh, we have the software testing, both manual and automated, right? So how do you think the automated testing works? So this symbolic execution can be used to generate the test cases. So that's how your automated testing tools will work. What it does is it will create input values that will cover all the possible branches in the program. So all the permutations will be created. How is it relevant to us? Who are we? We are from security, right? It is a very, very awesome thing if we know how to make use of it. And that's what we're going to learn today. For security testing, we can use symbolic execution to find the hidden vulnerabilities like SQL injection, insecure storage, privilege escalation, or any other by exploring the paths that we can make use of. And this is mostly used in the malware analysis in order to identify the hidden functionality or to find any suspicious behaviors. Let's focus on the security perspective and let us recreate this simple program for our understanding in terms of security. Let's take a simple login system as an example, and we can have a code like if password is equal to admin123, then we'll make the access to true, else we'll make the access to false. With symbolic execution, we will replace the password with a symbol P. So the symbolic execution will be able to find the condition where P is equals to admin123, which will give us the path access equals to true. And it also finds P not equals to admin123, which will give us the access equals to false. So it automatically generates the test inputs like this. Understand, we are not manually performing this symbolic execution. Okay, so we are talking about a software which will perform all these things, and this can be used as a replacement for manual analysis. Normally what we do, we look at the source code, we trace it one by one, we try to understand and figure out how the program works, right? So instead, we do this symbolic execution to understand or to help us understand much faster. So what will be the test inputs? We took the variable as P. So P equals to, we have the success factor, that is it should match admin123, correct? So this is for success. Then we have another path where we can give any input, anything, doesn't matter, other than admin123, it's a failure. Now, how can we use this symbolic execution in Android security? As I mentioned in the beginning, we will be using this symbolic execution to create a keygen that we can use to get access to a program, mainly the Android application. In Android security, we can use this symbolic execution to analyze the Android applications, which are basically the APKs. And we can uncover bugs, vulnerabilities, or security flaws either in a automated or semi-automated manner. And after understanding what is symbolic execution, we can say this is especially useful if we are dealing with the problems where we need to find correct input for reaching a certain block of code. So we can use symbolic execution especially if we want to find a correct input for reaching a certain block of code. It can be to crash the program, it can be to bypass the login, it can be to bypass the subscription. It can be anything of our choice, but we need to find the correct input to execute that block of code. So if we look at the keygens, where it will be generating certain set of keys which we can take it and use it to get the professional or paid version of the software. So unless we figure out that correct input, what is expected by the software, we cannot access the paid version. Hope we understood the symbolic execution and how we can, or what we can do in Android security. So enough of theory. As of now, we have some understanding of what is symbolic execution and where all it can be used and how does it help us in security testing. Now we will take a very simple challenge from Android Crackme, and the challenge name is Android License Validator. Let us solve a very simple example by taking an Android Crackme challenge called Android Uncrackable DRM, which is mainly called as Android License Validator. And we will be doing this using the Angr binary analysis framework, which is our main symbolic execution engine. So this is from the OWASP. You can come to OWASP mask crackmes. So here it is, and the file that we are looking for is Android Uncrackable DRM, which is having a file name validate, and it's a ELF file compiled for Android, and it's 32-bit. Let us download this. Okay, so we have downloaded the file. Now let's switch to our terminal. So what is Android License Validator? Let's say an Android app sparks your interest and you want to purchase a license for that app. But before you paying out for the license, you want to test it out, but we have no keygen available. Now our objective will be to generate a valid serial key or create a keygen that generates the serial keys which is accepted by this app. And this app is none other than our Android license validator, which we just downloaded with the file name called as validate. So what exactly this Android license validator does? Let's understand in brief so that we can get started. So this license validator will implement a key validation function in native code and is packaged as standalone ELF executable for Android devices. There is a difference between analyzing Java code and analyzing native code. Native code is more challenging than Java, which is why most of the critical business logic of the applications will often be written in the native code. So you might have checked so many applications, you never found much of the critical business logic, but the functionality exists, right? And we never bother to check the native code. The validator is also written in native code, compiled as ELF executable for Android devices. So we can apply this concept whenever we are dealing with the Android apps that include obfuscated native libraries. Obfuscated code is often put into native libraries specifically to make the process of deobfuscation more challenging. We have the backstory that we want to create a keygen and generate a license so that we can use the app without paying out. And the reason is the key validation function of validator is written in native code, which is more challenging and that is obfuscated. Before we get started, note this executable is compiled exclusively for ARM architecture. I understand it's ELF executable, but it doesn't run on your regular Linux. It's specifically for Android devices only. And this will not even work in your emulators like your AVDs, Genymotion, unless the ARM emulation is available, which these tools does not do it. So I recommend you guys to have a physical phone connected to your system so that we can follow along with the practicals. So now let us install this validator into our device, and the downloaded file is in our downloads folder. So let me quickly shift to my downloads. I'm in my downloads. Now I need to connect my device. So physically using a cable, and you need to enable the developer options. So if you don't know how to enable the developer options, you can go to your about phone, click on 7 times on your build number or any other Android versions. That will enable the developer options. And once that we have the developers options enabled, then go inside the developer options, click on USB debugging. Enable that. Once it is done, connect your phone to the system using the USB cable. You should get a authorization request pop up in your mobile device. Once you get that, click on OK or approve and you are good to go. So my device is already been connected. So let me check if my device is connected. Yes, it is connected, and if it is successfully connected, you should see the output like this. Now what we will be doing is that we will be copying the binary, ELF binary, into our Android device, make it executable and execute it and see how exactly it works. So we'll use the Android, we will use ADB push, and the file name is validate, which you should find it in your downloads folder. So I want to push this to any place, it's up to you, but I'm pushing it to my data local temp folder. You can see that it is successfully pushed, right? Now my next step is to make it executable. So ADB shell chmod data local temp and validate. Oh, sorry. Validate. Let me clear the screen so that we can check multiple execution paths manually. Okay. How do we execute? ADB shell, just call the file. So it's printing from the help section where we need to pass serial along with the file name. Currently don't have any serials as of now. So let's try something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 0 is sufficient. Incorrect serial, wrong format. Good thing is we have more information than what we need. We can figure out that incorrect serial is logical, but wrong format is something that we need to understand. The wrong format can be in terms of the number of characters or alphanumeric characters, symbols, or any other special character. So far, we know nothing about how a valid license key looks like. Now, in order to get us started, we need to do the reverse engineering of this ELF executable. And for that, we will be using a plugin called Iaito, which is for Radare2. So the disassembler we will be using is Radare2, which is CLI based. So we have a GUI plugin called as Iaito, and we'll be using that to do our simple yet complicated reverse engineering. So let's get started by switching to the Linux. So let's install all the prerequisites that we need to install Radar and the Iaito. Most of them are installed. Then the next command will be to download the Radar and install it. Now let's quickly clone and install the Iaito. As you can see, we are inside the Iaito folder. Now let's configure it. We'll run the command make. Now that our installation of Iaito is completed, let's actually install it. Sudo make install. This will install the Iaito properly. Now that our Iaito is installed, let's launch it. This is the initial interface of the Iaito, where we have file hex project. As we have a simple ELF file, in the file section, click on select and select the validate file and click on open. Then click on start and don't touch anything. We are using the default options to get started. So I hope this is sufficient for us. So simply click on OK. This is our initial view of the disassembled validate file, and here is the overview of it, where the file name is validate with the path format ELF. It's a 32-bit file, so class ELF32, mode read and execute, size is 9.14 kilobyte, type is din in the bracket shared object file. Remember this? Then it's written in the language C, then the base address is 0. Let's not go much deeper into all the components of this tool, which is not required for us to get our keychain prepared. Then architecture is ARM and machine is also ARM, and rest is Linux, and you can see the Indianness, it's little. So this is sufficient for us to get started, and if you scroll down, there are other information that we can get it from the validate, that after the analysis, this is the uh, statistics that it has come up with. There are 26 functions, 127 calls, 11 strings, 9 symbols, 9 imports. Now, if we come back here, we can see that the base address is 0, right? And this is because Iaito chooses to load the binary, that is the ELF file, at 0 base address. So I told you to remember the type dyn, shared object file, right? This indicates that the binary is PIE enabled. PIE stands for position independent executable. That means whenever a binary like validate is PIE enabled, that means the code that is compiled will be allowed to be loaded at any memory address. So that means, in simple terms, if you load this binary into the memory, there is no specific place this gets loaded. It can be any memory address, which is very random. That's why it's called position independent executable. Some executables are not position independent executables, which will ask for the same memory address. So that means this is something that we need to understand so that it can be helpful in our analysis. Now, what is this PIE and why it is used? We understood what is a PIE and what exactly it does. Now, this is a security feature. We'll be working with something called as ASLR, address space layout randomization, which you might have heard if you have done the mobile analysis, especially iOS and any other place. If you have ever done reverse engineering, then you might know how to get started, where to look for, what to look for. So we'll try to keep this as simple as possible. So if anybody doesn't know how to do reverse engineering, then they can still understand what exactly we are doing rather than simply taking them to the result. So remember that when we ran this validate file, we got errors, usage error, incorrect format. Remember that? So that is one thing that we can get started. And where can this be present? Mostly in the main function of the program. So if you ever wrote a program, you will understand that these kind of conditions will be often kept inside the main function. So it is very common for us to start the analysis with the main function because that will be the entry point of the program. In the left side section, you can see all the functions that have been present in this program, and we want to get started with the main function. But these functions are not the normal functions. These looks like it has been stripped. That means these function names are not context. They are not giving any context. So how do we identify the main function? The problem here is this binary is called a stripped binary because all the function names have been stripped, which will make our job more difficult. So our main function is not explicitly named. Here, if we come to the quick filter and type the function main, we don't get any items returned. That shows that we have no option to rely on the function names as they have been stripped. Now, how do we identify the main function? If you remember that when we ran the program, we got certain errors. This is part of main function according to our understanding, right? So if we can use that to trace back, then we may have a chance to understand the application. So what was it? It was incorrect format. So we'll go to the strings section and let us search for the string called incorrect serial. And here we can see there are only two results that are showing up. One is incorrect serial and the other one is incorrect serial wrong format. So let's double click on the incorrect serial wrong format because this is the one we have seen in our initial testing of the validate file or the execution of the validate file, not the other one. So let's double click on the incorrect serial wrong format, and this is how it should look like. Initially we started from the dashboard, then we moved to strings, and here we searched for incorrect serial because we wanted to find that specific string so that we can get started from there, assuming this is part of the main function. So once you double click, it goes to the disassembly tab. This is the tab. Here you can see that incorrect serial wrong format is present. And the address you can see here, it's 1A98. We need to understand the code surrounding this because this is a print statement. It is simply printing this string using the print statement. So let's analyze the code that is around this, which may contain our actual validation logic. The objective is to find the validation logic so that we can understand how the validation is being performed, so that we can create a keygen based on that validation. If we look down, there is nothing. So let's go up and see. Oh, okay. So here we found a section which looks very important for us, and that's because of the string entering check license. And we can also see product activation passed, congratulations, incorrect serial statements. So where did we come here so far? From string, we found the string incorrect serial wrong format, and we came to this specific address, and we wanted to check the surrounding codes. So we went down and there is nothing much. So we'll come back there and then we'll go up and see what we can find. Okay. So here is a section that we have few strings. One is product activation past and the other is incorrect serial. And here we have entering base 32 decode and we have outline. Then we have entering check license. These are our interesting strings which indicates that we are in the main function. Now, where it starts from here. The address 1834 has a simple command or the instruction where the opcode or operand is move, which indicates to move from one variable to the another variable, or in terms assembly, one register to another register. So here we are telling that move the register 0 to register 3. The structure of assembly instructions looks like this. This is the command and this is the destination and rest are source. So this entire instruction says move whatever is there in R0 to R3. And the next instruction CMP stands for compare, where R3, which is the source, is being compared to R4. Okay. So that means this R0 may likely hold the result of a validation function, which we are moving it to R3, and then that R3, which is the result of the validation function, is being compared with R4. And here R4 may be the expected value or the expected serial to successfully activate the product. BNE stands for branch if not equal. That means if these two registers are not matching, then it will go to address 1854. And if we look at address 1854, we can see the string incorrect serial. And that means we are going to the second execution path by skipping the first execution path where our product gets activated. Is this our starting point of the main function? Directly you are comparing something and then you are branching if it is not matching, and there are two print statements where it's showing one for success and the other one for incorrect. So that means this is not the start of the function. So let's go further down and see if we can find the start of the main function. So this all comes to the else statement. So this address space 1864, from here if we see that, we can see that there is a sub opcode, pop opcode, and this. If you do a quick Google search, this shows that these are the basic instructions which are called as functions prologue. Okay, these are the standard functions prologue. That means a few lines of code at the beginning of the instructions. And here we can see the pop command is being used to clean or restore all the registers. Before the start of the function, all the registers or the variables has to be cleaned. If we come down here, 1874, right? Here we can see there are push, add, and sub commands, which looks like that this is setting up the registers. For example, here push is setting up the new frame pointer. Okay. So let's not go much deep into the assembly. Let's stick with this basic understanding that here we can see that things are getting restored or cleaned up. And if we just do a quick Google search, we can find that this is something called as functions prologue. That means it's a simple few lines of code at the beginning of the function. So that means our function is getting started, right? And the next instructions shows that we are setting up the new frame pointer. This is a command or opcode. This is the destination and this is the first source. This is the constant. That means our 1874 is the actual main function address. Let's not bother about the function prologue, but this is where our frame pointers are getting initialized. So our main function starts from 1874. But let us still verify by analyzing the code or the instructions further below. So if we look at the instructions 1880 and 1884, these are the two instructions which are saving the command line arguments, okay, into register R0 and register R1, okay. And if we come down and see these three instructions 1888, 188C and 1890, let me scroll up. If we look at these three instructions, here we are loading the argument into the R3 register, and then we are comparing 2 with R3 and we are branching if equal. That means if argc equals to 2, that means we have received two arguments, then you can branch. In short, this program will check if the user has provided one argument at least other than the program name. If not, it will exit or it will print the usage instructions. If you remember, we have seen that when we simply run the validate, we get this particular message saying usage. That is the usage instructions where it is showing us that additional argument has to be passed. So this is where it is being compared and decided what to do next. So this concludes or confirms our beginning of the main function, that is 1874. So this is our main function starting. Now that we have identified our main function or the entry function, we will also try to identify the code regions which are suitable for our symbolic execution. So let's start by identifying the first section where we need to check for the size of the argument that we need to pass. And here we have this instruction which indicates that this is the first code region that we need to focus on, as this is performing the length check of the argument. So from here, if you see, we are going to 1898, that is here, right? So we need to come all the way to 18B4. This entire section is responsible for performing the length check of the argument. With the same format, try to understand this instructions and what they are doing. But for us, this is sufficient enough to say that this string length is checking for the length of the string, right? So if you want to understand this, you can check it and understand what exactly they are trying to do, or use ChatGPT or any other AI to help you understand these instructions. Okay. Then the second code region that we want to look at is entering the base 32. These are just the strings. So let's come down, and here is the function. We can see that our next focus point or the code region should be here, which is the function to perform the base 32 decode, right? And then we have the check license, where the function is main check license. How? See the term, and we can say this is like print statement entering base 32 decode. That means the function is called later, right? And directly the function is here. So this will be our second focus point or the code region. And here it's entering the check license. After the statement, function call should be there. So this will be the third function call. So what did we find out so far? This is one code region where our length of the argument is checked. Then here is the second code region where our base 32 is being decoded. And then here is the third code region where we are entering the function to check the license, right? So in short, str length, that is string length, is called at the offset 18A8. Remember these addresses. So when we actually create the program to perform the symbolic execution, we need to make use of these address spaces. Okay. So 18A8, where the string length is being called and the return value is being compared, to 10 at offset B0. So string length is being called at offset 18A8 and its return value is compared at 18B0 to 10. Okay. Immediately after that, you can see the input string is being passed to base 32 decoding at the offset 1840. Okay. So in short, we have this string length being called at offset 18A8 and the returned value is compared with the 10, and this is at 18B0, and immediately after that we are passing the input string to the base 32 decoding function. Base 32 decoding function, which is at offset 1340. And this provides us with valuable information that the input license key is a base 32 encoded 16 character string. Why? This is what it says. This is total 10 bytes in raw, which is 16 characters in decimal. Okay. So as of now, what we have understood is that the license key is a 32-bit encoded 16 character string, and we derived this value from this because 10 bytes in raw converted to decimals is 16. The decoded input is then passed to the function at the offset 1760, which will be validating the license key. So we till now understood that string length is being checked at so and so, that is 1888, being compared with 10 bytes, and then it is passed on to the function at 1340, and then we are concluding that the input character is 32-bit encoded 16 character string, and that decoded input is then passed on to 1760 function to check the license. The function 1760 is having the core validation logic. So let's go to the graph view and see the flow and the instructions together. Let's double click on the function, which will come to here at the top of the function, and switch to the graph section. So here is our focus point where our function is starting from 1760, and there is a loop that is present at 1784. You can see it here. Okay, which is performing the XOR operation. Can you identify where is the XOR operation? So this loop is specifically performing the XOR operation, which is at 1798, and this is to check if input serial matches a specific pattern. If you know about XOR, XOR is a very commonly used technique in order to encrypt the information, where our goal is to perform the obfuscation rather than the security. So XOR should not be used for any serious encryption because it can be cracked using like frequency analysis. Therefore, the basic existence of XOR encryption in this kind of validation logic should be your special attention caller. So what you could have done, you could have come to the function, and this is the start of the function, right? It is more simpler for us to view this in the graph so that we can see everything, but at the end it's both same even if we view it in the disassembly. Now if you simply scan the instructions, what is the instruction that requires your focus? This looks like normal instructions. There is no operation which is happening. Then where do we need to focus? Got it? So why we came here directly is because of the presence of XOR. Now let's come to this side and let's see what is there in the 17 DC section. So for that we need to understand these instructions. Here we can see that we are comparing R3 with 4, right? And then we are branching, correct? So this branch is coming to 1784 where we have the XOR operation. So here we can see that at the offset 17 DC, the XOR value, the XOR decoded value obtained from the above is being compared, against the return value from a sub function which is at 17 E8. So here we have 17 DC, right? And here we have the function 16F0, which is a sub function which is being called at E0, and it is being compared. So at 17 DC, we can see that the XOR decoded value which is obtained from the above is being compared against the return of the sub function at 17 E8. So we are getting it for R4 right? And the result we have is with R3, and we are comparing R3 with R4, and we are branching if not equal. Now, clearly this function is not complex and can be analyzed manually, but this is still a heavy task. Especially if we take up a very big code base, this will become a major constraint. And this section would be great to automate. Dynamic symbolic execution is helpful in exactly these type of situations. The symbolic execution engine will determine each byte of the input string by mapping a path between the first instruction of the license check, which is at 1760, and the code that prints the product activation past, which is at 1840. So the constraints which are obtained from these steps are passed to a solver engine which finds an input that satisfies them, which will be our final valid license key. With this, we will start with coding or actual use of symbolic execution engine and perform the same steps. And for this, we need to perform several steps in order to initialize the symbolic execution engine called Angr. Angr is the symbolic execution engine that we will be using for this validate executable. So what do we need to do? That we will see by writing the program. We came back to the terminal. Let me close the decompiler. Not gonna save it. Let me clear the screen. And the language that we will be using here to perform this symbolic execution will be Python and using the engine called Angr. Okay, let me do one thing. Let me come back to home and create a script called symbolic with the extension py. First, let's import Angr and base 64. Why? We need to encode the input string into base 32. So we have imported whatever we need. Now we need to configure the options. As of now, we will configure empty. These options are needed so that we can pass it to the Angr later. We need to perform several steps to initialize Angr's engine, right? Now here comes our first step, that is load the binary into a project, which will be our starting point for any kind of analysis in the Angr. Now how do we load? We'll give some variable Angr dot project, and the binary is validate, the same way that we have loaded our validate into Iaito is the same way that we can load by passing the file name to the Angr. And the load options will be same as we have defined above. Next, we need to pass the address. This is the second step. So we need to pass the address from which the analysis should start. We can either pass it from base 60 to base 32 implementation, or we can directly jump to the actual serial validation function. Now, base 32 implementation, there is nothing for us to do. It's common. So there is no point of us taking that and making the program more complicated and time taking. So we can skip the base 32 implementation and directly go to our serial validation. Correct? If we remember, we were at the place where we took the input, compared it with string length, then passed it to base 32 encoding, then we got the output of it, and then we passed it to the serial validation function. So we are skipping the base 32 implementation so that we can directly go to the serial validation function. So our analysis should start from serial validation function to keep it simple and easier. So how do we pass, and what is the function address? So the key validation or the serial validation function was starting at serial validation function starts at 1760. Correct? So that's where we will be creating the initial state. And we are coming to this just because we can bypass the base 32 encoder, which can speed up a lot of things. Okay, as of now, let's comment this and let's define some options for our Angr. And that options will be Angr.options symbol fill unconstrained memory and zero fill unconstrained registers. These are the two options that we will be using for this symbolic execution. Here, symbol fill unconstrained memory. We will be passing this option because when we run the Angr, we will be generating lot of warnings about memory. And most of the time, this memory warnings will not be of help. So we just want to avoid all the clutter. We are using this option. And the next option is zero fill unconstrained registers. This is to fill any unconstrained register with zeros. Okay. So as we have configured our options, let's move ahead and define the state. B factory. We are defining the blank state which starts at address 0401760, and we will pass these options to the state. So why are we taking 401760? What is this number? Whenever we load an executable which is PIE enabled, where we saw it in the beginning of the Iaito, the binary was tagged as dyn shared object. That indicates PIE enabled. That means it can be loaded at any memory address, right? So whenever we load these type of executables, the Angr will load them with a base address of 4. So if you remember in the Iaito it was 0 and the Angr will load them at starting with 4. That means with whatever is our understanding, we need to add this 4 accordingly to match the offsets of Angr. Okay, so whatever we get the offsets from Iaito has to be modified to match this base address before we pass to the Angr. So that means here the serial that we got from Iaito has to be transformed into 401760, and the reason is our base was looking like this. Okay, now we have our answer of why we have to use 40. Let's continue further and call the simulation manager. A state is defined. Now let's call the B factory simulation manager. We will pass the state and then we will start exploring and find 401840 and avoid 401855 and 4. So what we want to find is 1840, which is the address of product activation past, right? That's what we want. And what we want to avoid is that 1854 where we get the error message incorrect serial. If you're not sure, you can go back to the disassembly and you can check the address 1840 and 1854. Now that we have defined what are we looking for and what we want to avoid, let's continue further. And this is the third step where we are passing the offset 1840, where the code responsible for it is printing the product activation past message. And then we have the step 4, that is at 1854, where the offset having the code block prints incorrect serial. So these are the 4 steps that we need to initialize the Angr. One is load the binary, and this is what we are doing. Then we need to skip the base 32 and directly go to this specific address. And what is this address? This is the first instruction of the serial validation function. Okay, this is the second step. Then the third step is to go to the offset where we want the execution to show product activation past, and we don't want to see the message which is located at the 401854. These are the 4 steps that we need to perform to initialize the Angr symbolic execution engine. We'll complete the program. Found mgr found 0. We need to get the solution from address equals to found dot memory dot load and found dot registers dot r11 and 020 comma 1 and ns equals to little concrete address found solver eval address. You don't need to understand all these things. This is just the basic closing of the program. You just need to note that here I have mentioned the little Indian because our program was little Indian. Okay. Solution found solver eval found memory load concrete address 10 cast 2 bytes. And finally we have the print B32 encode the solution. Now what exactly this Angr solution script does? This Angr looks at all the different ways a program might run based on the input, and it builds a kind of binary tree or a decision tree showing every possible path the program could take. And for each path, it creates a math equation that will be describing the conditions needed to follow that path. And then Angr sends these equations to a solver which figures out real input values that make those paths happen. And at the end you can see the successful paths, the one that we are interested in simulation manager dot found. If we look at the script, what's happening in the script is the script is trying to figure out the correct input, that is our license key, that makes the program says activation successful. And the key clue that comes from the function at offset 1760, which checks if the input is valid or not. Now inside that function, the input string is passed into register R0 and is saved to a local variable on the stack at fp 020. Now we are using the same to ask Angr's solver that what input value must have been here to reach the success state. Getting it? So that is why we are giving this value and passing it. Now in ARM v7, that is the latest ARM version, R11 is the frame pointer. Now if you look at the stack, in the stack it was like FP hyphen 0 into 20, right? Now how do we write that? Now FP is for frame pointer and R11 is the frame pointer in ARM v7. So our this entire points to the exact spot where the input string is being stored. Now that's how the script will be able to know where to look for the solution. Now we'll save the program and then we'll run and see how the output looks like. Let's create a folder SK for serial key and let's switch into that. We are inside the folder, right? Now let us move both the files symbolic and validate to this folder. And here we have both the files and both are in executable state, right? But there is only one problem. Till now we did not install the Angr. For that I will be creating an virtual environment. Python 3 -m venv and I'll call it as env. So my environment is ready. Let me source it. I have activated. Now I need to install the Angr. And I am installing specific version which is 9.2.2. Even the latest version should work out. If in case it doesn't, you can fall back to this. So I'm not showing the latest version. So let me install it. And we are done. So let's try running our symbolic. And here we have an error which is very common. So we'll see how to fix this. So in order to fix this common issue, we need to downgrade our protobuf version to the specified numbers. And let's install that. Pip install protobuf 3, 2, 3. And the version I'm taking is from this or lower. Okay. Let's see if this will fix our problem. Let's run the file and see what the output will be. Python 3 symbolic and enter. Okay, great. So still we have few warnings. This is why we were using the options of two unconstrained memory and unconstrained registers, right? So it's okay. Now if you see The main binary is a position independent executable. It is being loaded with a base memory of 4, right? That's why we loaded the binary with prefixing this as base address. But if you see here, we have got our answer, which is the 16 character string. Now this is our serial key. If you are trying by watching this video and you got a different value, don't worry, there will be multiple keys. So there is no need to have the same key. The key may change. Okay. Now what do we do? Let's take the key. Let's go back here and let us pass the same key here with this command. This is our key. You can see that we have successfully activated our product. Congratulations. With this, we have understood the symbolic execution by practically performing the execution using the engine called Angr on a ELF binary, which is a 32-bit PIE enabled, and this is part of our mass crackmes, which is Android uncrackable, and the file name is validate, and it is Android license validator. So if you have any questions, if you did not understand anything, if you want me to select a topic and then make a video on it, comment it below.